video, we are going to talk about simple pendulums. So first, let's go ahead and define a simple pendulum. So a simple pendulum is just a pendulum that oscillates at a small angle theta back and forth. So again, theta will have to be relatively small angle. It doesn't work for huge angles, so it's relatively small. And we'll have just the pendulum just going back and forth like that. And again, the period is the time for one complete oscillation. So going all the way to one side and then all the way back to another side. So simple pendulums, by definition, is whatever the object is that, so we have some object of mass m. It could be like a coffee cup that might have been broken at some time. It could have been a tennis ball. It could have been anything. Some mass that is attached to a string that is massless. So this is a massless string. And there's some little point mass, whatever you choose it to be, like a mug, ball, whatever. Cool. So that's a simple pendulum. So a couple things I'd like to define for a simple pendulum. So one thing, the amplitude, we're just going to call that the angle from the max point to the equilibrium point. L is going to be length of string. So it's the distance of the object of mass m to the pivot point. So that's the length, m. And then a pendulum will be on Earth or somewhere else. So g is going to be the acceleration due to gravity. Okay, so what I'd like you to do right now is I would like you to design an experiment to go ahead and figure out what factors affect the period of a pendulum and choose what you think the appropriate period is. So you can design the experiment however you'd like, collect some data. So I encourage you to take some sort of string, tie a mass to the end of it, go ahead, do some good old measurements, and then I have 6 equations right here. You can go ahead and guess which equation is correct. So go ahead and pause the video right now, go ahead and design an experiment, and then choose an equation. And when you get back, once you unpause the video, I'll go ahead and circle the correct equation. And again, I want to remind you that simple pendulums only work for small angles. So make sure your pendulum is not pulled back a big angle theta. Make sure it is a relatively small angle theta that the pendulum oscillates back and forth between. Okay, go ahead and pause the video, and I'll circle it when you get back. Okay, so the answer to your lab, and who knows, it'll be cool to see if it worked out that way, is, drum roll, this is the correct equation for the period of a pendulum. So cool thing is, amplitude doesn't matter at all, and the mass that you attach to the pendulum doesn't matter at all. Wow, pretty nifty. So again, L is the length of the pendulum. G, little g, is the acceleration due to gravity at whatever location you are. And T, period, is the time for one complete revolution. Great. So go ahead and write down that equation. We'll use it soon. Okay. So now we're going to go ahead and use the equation for a simple pendulum that we just learned. Period equals 2 pi square root of length over acceleration due to gravity g. Great. And then go ahead and solve the good old physics problem. Cool. So sorry, my writing, whatever you call it, covered some of the problem. That's not good. Cool. So what I'd encourage you to do, go ahead and write down this problem on your own piece of paper. Go ahead and try solving it whatever way you see. And then you can go ahead and watch my video to see if you did it similar way to I did, totally different way, or if you have any questions, you can use this video to help you out. And it's cool to see lots of different ways to solve a problem. Cool, so go ahead, try solving this problem, pause the video, and then you can resume. Cool. So first thing I do after I try the problem, so I think about what are we looking for? Okay, so we're looking for acceleration due to gravity on the other planet in terms of g. Cool. So let's go ahead and write down our relevant equation. So we know we're dealing with simple pendulums. So that equation is 2 pi square root of L over g. Cool. So we're trying to find the acceleration due to gravity on the other planet. So I'm going to take this equation and I'm going to go ahead and solve for g. Great. So go ahead. You can do some good old math to go ahead and do that. So let's see, first thing I'm going to do is I will square both sides. So I have this equation. Let's go ahead and just square both sides. Cool. So now I have, let's see, t squared equals, make sure you're squaring each term, 4 pi squared L over G. Cool. Now I will go ahead and do some more math. Let's see. Multiply both sides by G, and then I can divide by t squared. So G equals 4 pi squared L over t squared. Great. So that gets acceleration due to gravity by itself because that's what we're changing. Cool. So I'm going to do this problem all without a calculator just because I think it's fun to do. So on Earth, so I'm going to write that. So on Earth, the period is 3 seconds. And G on Earth is just G. Cool. So this other planet, so I'll call this planet nu, the period is now 6 seconds. And G nu is what we want to find. So I'm going to go ahead and think, what factor is the period increasing or decreasing by? Okay, if I look at it, it looks like it's doubling. It's going from 3 seconds to 6 seconds. So period nu is going to be 2 times period on Earth. Great. So, okay, I'm going to take my equation that I just made to get acceleration due to gravity. So again, that equation is G equals 4 pi squared L over t squared. Cool. So now what I'm doing, and again, so let's say this was originally talking about Earth. So I'm going to call this G on Earth, and this is T on Earth. Now, and this is the length on Earth. Cool. So the new place to go to, I'm going to call it G nu. So same idea. It's 4 pi squared L nu over period nu squared. So let's see how that compares to the Earth, what we were talking about. Cool. So 4 pi squared, that just stays the same. L, is the length of the pendulum changing? Nah, that's going to stay the same no matter where you go. So I'll call that LE. It's going to be the same thing as Earth. T nu, we just said that's going to be 2 times bigger than what it is on Earth. So I'm going to put in 2 T and square that whole thing. Great. So what I'm going to do, I'm going to go ahead, square the bottom, distribute that squared. So this is going to be 1/4 TE squared on the bottom times 4 pi squared LE. Great. So this whole term right here that I'm highlighting right there, that is the exact same thing as what the acceleration due to gravity is on the surface of Earth. So I can look at it. It looks like I'm changing it by 1/4. So the answer is just going to be 1/4 of G, or whatever it is on Earth. So I'm decreasing acceleration due to gravity. The acceleration due to gravity is decreasing by 1/4 compared to what it is on Earth. Great.